Today we are going to discuss about signal to noise ratio calculation in matched filter. Actually, this is a part of the syllabus digital communication. Both minor course, that is ECT 284 minor course digital communication and EC 302 digital communication contains this topic. Okay, so both of the minor students also refer this topic. So signal to noise ratio calculation in matched filter. In the previous video, we have discussed about a matched filter. Okay. So now we want to calculate signal to noise ratio, how the signal to noise ratio is improved in the case of by using matched filter. Okay. So what is signal to noise ratio? It is actually signal power divided by noise power, right? So we have to calculate the signal power first and then we have to calculate the noise power. Okay, so let us see. In the case of a communication channel, we know that white noise is included or white noise is added along with the signal component. So we can say that let the input signal is phi of t and it is passing through the channel, and whenever it is passing through the channel, a noise is added here. So the noise here added is white Gaussian noise that we have discussed in the previous video. Okay, you can refer the previous video regarding the AWGN channel and matched filter. Okay, so you will get a base. Okay, so here phi of t, actually this is the input, that actually this phi of t represents the orthonormal basis function. And for the case of minor students, there is no need to study the orthonormal basis function. Actually, it is calculated by using different steps, and it is orthonormal basis function is calculated by using signal component. Okay, so it itself represents a signal component. Okay, so it represents the signal part of the input signal. Okay, and whenever it is passing through the channel, a noise is included. So the output of this channel is represented by x of t. Okay, so x of t is, what is x of t? X of t contains phi of t and noise w of t. Okay, so we can write x of t equal to phi of t plus w of t. So this is the input signal received at the receiver. Okay, we can say like that. So we know that matched filter is used to reduce the effect of noise, or it is used to improve the signal to noise ratio at the receiver side. Okay, so we have to use a filter. Actually that matched filter is a linear filter. We can say it is a linear time invariant filter. Okay, so we are giving x of t to this filter. So of course we know that in the case of when we are doing analysis, a linear filter will have some impulse response. What is impulse response? Whenever an impulse is given to that filter, it will produce an output. So that is the impulse response of the filter. So let us represent that impulse response as h of t. Here filter will have an impulse response h of t. What is its meaning? Whenever an impulse is given to the input of this filter, the corresponding output is called a response. Okay, so that is h of t is the filter response for an impulse. That you should remember in mind. Okay, next let us analyze. Here the incoming signal x of t will have a signal part phi of t and a noise part w of t, right? That is obtained from this relation. So whenever phi of t alone passing through this linear filter, what will be the output? That output is phi 0 of t. This is all are simple notations. Okay, so whenever phi of t is giving to, phi of t alone is giving to this linear filter, actually this is a matched filter for reducing the noise. Okay, so phi of t is giving to this filter, then the corresponding response is phi 0 of t. Whenever noise is giving to this filter, the corresponding response is n of t. See, okay, you remember what are the notations? Phi 0 of t is the response of the filter corresponding to the signal part, and n of t is the response of this filter corresponding to the noise part. Okay, so here you know that linear filter, here the input is x of t and output is y of t. So this y of t will have the component, what all are the components? Phi 0 of t and n of t, because its input is phi of t plus w of t. So the linear filter output will contains the response phi 0 of t and n of t. That I have represented here. Okay, so we can write y of t is the response due to phi of t and the response due to noise. Okay, so we can simply write y of t equal to phi 0 of t plus n of t. So here is the equation y of t equal to phi 0 of t plus n of t. Okay, so for LTI system, output is equal to the convolution of input and impulse response. See, if you are an electronic student, so you might have studied that in the case of a filter, we can write the output is equal to input convolution impulse response. So that is a basic equation. So if you have a base of the signals and system subject, then you know that output can be represented by the convolution of input and impulse response. So that you should remember. If minor course students doesn't know that, you should also note that point. So output of the filter is the input convolution impulse response. So let us continue. So for the LTI system, so here what is the LTI system? This is the linear filter is an LTI system, linear time invariant system. Okay, so phi 0 of t, we know that phi 0 of t is the response due to the signal component. So what is phi 0 of t? This is phi 0 of t. So how we are obtaining phi 0 of t? We are giving phi of t as the input. So phi 0 of t can be represented by the input convolution h of t. So phi of t convolution h of t. Similarly, n of t will be equal to w of t convolution h of t. So that is that is a simple convolution equation when we are using filter. Okay, so we can write phi 0 of t equal to phi of t convolution h of t. So this symbol is convolution. Okay, so what we are interested is we have to find out the signal power. So here the signal component is this one. Okay, so its power we have to measure. So നമ്മളിപ്പോൾ ഒരു ട്രാൻസ്മിഷൻ നടത്തുന്ന സമയത്ത് ഇൻപുട്ട് സിഗ്നൽ വരികയാണെങ്കിൽ അതിൽ നിന്ന് നോയ്സും കൂടി ആഡ് ചെയ്തിട്ടുണ്ടായിരിക്കും. അപ്പോൾ ഫിൽറ്ററിൻ്റെ സിഗ്നൽ ടു നോയ്സ് റേഷ്യോ കാണണമെങ്കിൽ അതിൻ്റെ സിഗ്നൽ പവർ കാണണം. അപ്പോൾ ഇവിടെ സിഗ്നൽ കമ്പോണൻ്റ് ഏതാണ്? phi of t ആണ് സിഗ്നൽ കമ്പോണൻ്റ് എന്ന് പറയുന്നത്. ഓക്കെ, അപ്പോൾ അതിൻ്റെ പവർ നമ്മൾ കണ്ടുപിടിക്കണം. ആ സിഗ്നൽ പവർ നമ്മൾ കണ്ടുപിടിക്കണം. അതിന് വേണ്ടിയിട്ടാണ് നമ്മൾ ഈ ഇക്വേഷൻ എടുക്കുന്നത്. സിഗ്നലിൻ്റെ കമ്പോണൻ്റ് ഏതാണ്? ഇതാണ് അല്ലേ. അപ്പോൾ ഫിൽറ്റർ ഔട്ട്പുട്ട് ഈസ് phi 0 of t. So Fourier transform of this phi 0 of t is equal to what? Fourier transform is represented by, actually this is time domain equation and Fourier transform is frequency domain equation. So the variable will be changing to frequency f. So phi 0 of t will change to phi 0 of f. Similarly, phi of t will be changing to phi of f and h of t will be changing to h of f. So whenever we are taking the Fourier transform, convolution operation will be changing to multiplication operation. So phi 0 of f. So the Fourier transform of phi 0 of t is phi 0 of f. So phi 0 of f equal to phi of f into h of f, and we can take any order. Okay, h of f into phi of f. So h of f is the transfer function of the linear filter. What is the time domain representation of filter? H of t is the impulse response and h of f is the transfer function of that impulse response. So phi 0 of f is equal to h of f into phi of f. Okay, so here h of f is the transfer function of linear filter. So the inverse Fourier transform of this phi 0 of f is equal to phi 0 of t. So inverse Fourier transform of phi 0 of f is equal to phi 0 of t. That will have an equation. What is the basic equation for the inverse Fourier transform? That is integral minus infinity to plus infinity phi 0 of f into e raised to j 2 pi f t into df. That is the basic equation. Okay, so frequency domain function into e raised to j 2 pi f t, that is integrated over the limit minus infinity to plus infinity. That is the Fourier transform equation. So phi 0 of t can be calculated by using this equation. But here phi 0 of f is what? That is h of f into phi of f. So phi 0 of t equal to integral minus infinity to plus infinity phi of f into h of f we can substitute here, and e raised to j 2 pi f t into df. Okay, so this is the time domain equation. Okay, so this is the signal component. So we have to calculate its signal power. Okay, so if the value is sampled at t equal to capital T, then phi 0 of t becomes, suppose it is sampled at a value t. See, this is a continuous function, and if we are taking the sampled value at t equal to capital T, so we have to substitute capital T instead of t. So we can write phi 0 of capital T equal to integral minus infinity to plus infinity phi of f into h of f into e raised to j 2 pi f into capital T into df. That is the equation. So here the signal power, so that is the sampled value at a particular time t. So then we have to find the signal power. So actually the signal power is modulus of phi 0 of capital T whole square. So that is the signal power. So for calculating the signal power, we are doing all these steps. Okay. So signal component is phi of t. So the signal power is modulus of phi 0 of t square. So we have to calculate its value. Okay. What is the modulus value? When we are putting modulus square here, we have to also put modulus square on the right side also. So the equation will become modulus phi 0 of t square equal to modulus of integral minus infinity to plus infinity h of f phi of f e raised to j 2 pi f capital T into df square. So this is the modulus equation. So actually this represents the signal power. So signal power is obtained. Next, what we have to do? We want to calculate the signal to noise ratio. So signal power is obtained. Next we have to calculate noise power. Okay. So that is the steps we are going to do. So you know that noise is random in nature, right? It will have different values. So for calculating the noise power, it is difficult to take each and every value. So we are taking, there will be an equation for calculating the noise power, that is noise power equal to integral minus infinity to plus infinity power spectral density of output noise into df. So we have an assumption that here the noise added is a white noise, white Gaussian noise. So from the experiments, it is proved that the power spectral density of the white noise is n0 by 2. Okay. So what is the noise power? The integral of power spectral density of output noise. So we have to calculate only the power spectral density of the white noise. So what is its value? n0 by 2. So we can directly substitute its value. So actually the power spectral density of the output noise is equal to n0 by 2 into modulus h of f square. Here you know that we are including a matched filter. So here what we are doing is we are giving the noise signal itself passing through the filter. Okay. So we have to incorporate filter response also. See, you know that x of t is passing through this linear filter. X of t will have a component input signal and noise. So noise itself is passing through this filter. So power spectral density of noise, white noise, is n0 by 2. So that noise is passing through the filter. So in order to write the equation for power spectral density of the output noise, we have to include a component h of t. Okay, so what is the power spectral density of the output noise? Output noise means the noise passing through the filter. Okay. So then we will be getting the output noise. So output noise power spectral density of the output noise is equal to n0 by 2 into filter response. What is filter? Fourier transform. That is impulse Fourier transform of the impulse response. What is its value? H of f. Okay. So n0 by 2 into modulus of h of f square is the power spectral density of the output noise. So simply white noise power spectral density will be equal to n0 by 2, but the power spectral density of the output noise will be equal to n0 by 2 into modulus of h of f into whole square. So we have obtained the power spectral density. Next, we have to calculate the output noise power. So what is its equation? This is the equation. Okay. So we can calculate the power spectral density of the output noise. So it will be equal to integral minus infinity to plus infinity n0 by 2 into modulus of h of f square into df. So that is the equation. So noise power we have obtained. So signal power we obtained and noise power is also obtained. Now we can write the equation for signal to noise ratio. That is signal to noise ratio is equal to signal power by noise power. What is signal power? It is obtained from the 6th equation and noise power is obtained from the 8th equation. Simply substitute that equation. Okay. So signal to noise ratio is equal to modulus of integral minus infinity to plus infinity h of f into phi of f into e raised to j 2 pi f capital T into df modulus square divided by noise power is n0 by 2 into integral minus infinity to plus infinity modulus h of f square into df. Okay, this is direct substitution, but we have to get the signal to noise ratio value. So for that we are using an inequality, that is Schwarz inequality. Actually this modulus value is not a single value, it is a combination of two functions. So we can apply an inequality. What is that inequality? That is Schwarz inequality. That is, what is Schwarz inequality? Actually Schwarz inequality is applied to this type of functions. That is, whenever the function is in the form of product of two functions and we are integrating over a particular integral, and its modulus value will be, so modulus of integral minus infinity to plus infinity p of f into q of f df square. So this is a, if it is a function, then we are applying Schwarz inequality to this. That means then this function, if p of f and q of f are complex conjugate pairs, then we can apply this Schwarz inequality, that is that will be less than or equal to integral minus infinity to plus infinity modulus of p of f square into df into integral minus infinity to plus infinity q of f square into df. So p of f ഉം q of f ഉം കോംപ്ലക്സ് കോൺജുഗേറ്റ് പെയർ ആയിട്ടുള്ള രണ്ട് ഫംഗ്ഷൻസ് ആണെങ്കിൽ ഇങ്ങനെയുള്ള ഒരു മോഡുലസിനെ നമുക്ക് ഷ്വാർട്സ് ഇനീക്വാലിറ്റി വെച്ച് ഇങ്ങനെ എഴുതാം, അതായത് സ്പ്ലിറ്റ് ചെയ്ത് എഴുതാം. പി ഓഫ് എഫിൻ്റെ മോഡുലസിനെ സെപ്പറേറ്റ് ആയിട്ട് ഇൻ്റഗ്രേറ്റ് ചെയ്യാം, അതുപോലെ തന്നെ ക്യൂ ഓഫ് എഫിൻ്റെ മോഡുലസിനെ സെപ്പറേറ്റ് ആയിട്ട് ഇൻ്റഗ്രേറ്റ് ചെയ്തതിന് ശേഷം അതിൻ്റെ രണ്ടിൻ്റെ പ്രൊഡക്റ്റ് എന്ന് പറയുന്നത് ഈ ഒരു ഇനീക്വാലിറ്റി ഈ ഒരു ഫംഗ്ഷനേക്കാളും കൂടുതലോ അല്ലെങ്കിൽ ഈക്വലോ ആയിരിക്കും. അങ്ങനെ ഒരു ഇനീക്വാലിറ്റി നമുക്ക് ഡെവലപ്പ് ചെയ്തെടുക്കാൻ പറ്റും. സോ ഇഫ് the above function, that is numerator ആണ് നമ്മൾ നോക്കുന്നത്, above function that is h of f and phi of f are complex conjugate pairs, that is h of f equal to k into phi star of f, ആ രീതിയിൽ നമുക്ക് എഴുതാൻ പറ്റുമെങ്കിൽ so we can apply Schwarz inequality to this function. Okay, so we can say here in this inequality p of f and q of f are any pair of real or complex functions, and this inequality holds good only if p of f equal to k into q star of f, where k is an arbitrary constant. Here we can, here q star of f, what is the value of q star of f? Q star of f in this function is phi of f into e raised to j 2 pi ft. Okay, so we are applying Schwarz inequality to this function, so we can split this functions as modulus of integral minus infinity to plus infinity h of f square into modulus of integral minus infinity to plus infinity phi of f into e raised to j 2 pi ft square into df, that is the function. Okay, so we are applying that Schwarz inequality. So here we are assuming that p of f value is equal to h of f, so h of f is similar to p of f, this p of f, and phi of f into e raised to j 2 pi ft is similar to q of f. Okay, so we are taking that value, so we are making that substitution and we can apply Schwarz inequality. So this modulus value will be less than or equal to, we can splitting that values. Okay, so that is similar to the previous equation. Okay, we are simply applying this equation over here. Okay, so next, here this function contains multiplication of two values. So here modulus can be separated. So we know that modulus of e raised to j 2 pi ft, that value equal to 1. What is the modulus value? Actually modulus, suppose if there is a function like a plus ib, that is an imaginary term, then its modulus will be square root of a square plus b square. Similarly, modulus of e raised to j 2 pi ft can be written as, what is e raised to j? We know that e raised to j theta equal to cos theta plus j sin theta. So what is its modulus value? It will be square root of sin square theta plus cos square theta. So its value will be equal to 1. Okay, so simply we can write that value equal to 1. So we can rewrite, or we can rearrange this equation as this left side will be less than or equal to this modulus value into, what is its value? This value will be equal to 1. So what is its value? This is equal to minus infinity to plus infinity modulus phi of f square into df. So this inequality changed to this form. So numerator will be changing to this form. So we can simply write a signal to noise ratio. See, signal to noise ratio. Here is a mistake. Actually, when I am editing it, some of the portions of the equation is lost. So the actual signal to noise ratio is less than or equal to integral minus infinity to plus infinity h of f square into df into integral minus infinity to plus infinity phi of f square into df divided by, what is the denominator term? That is as that of previous one, that is n0 by 2 integral minus infinity to plus infinity modulus h of f square into df. In short, we can say that actually we are changing the numerator terms by using Schwarz inequality. Okay, so that is the signal to noise ratio. So we can cancel the common terms. So this and this will be cancelled out. So the numerator will contain only the signal component, that is integral minus infinity to plus infinity modulus phi of f square into df, and here is a term at the denominator n0 by 2, so it will be changing to 2 by n0. So what is the final equation for signal to noise ratio of the matched filter? Signal to noise ratio equal to 2 by n0 into integral minus infinity to plus infinity modulus phi of f square into df. So whenever we are using matched filter, the noise part is eliminated from the, you can see this from this equation, okay. Noise part is not accounted in the signal to noise ratio. That means the signal to noise ratio is improved by using matched filter. That is the point we have to remember here. So we are using matched filter for reducing the noise or for increasing the signal to noise ratio. So here the final equation for signal to noise ratio is this one. So that contains a signal part alone. Actually this phi of f is a orthonormal basis function. So that is corresponding to the signal. Actually that orthonormal basis function is calculated by using signal component. The signal component. So signal to noise ratio improved here. So signal to noise ratio depends only on signal energy of the input signal, and power spectral density of the white noise is n0 by 2. See, n0 2 by n0, that is the only component. And the equality, this equality holds good only when this equality in this, that means actually this is an inequality less than or equal to. So equality holds good only when h optimum of f equal to k into phi star of f into e raised to minus j 2 pi f into t. So this is a condition. What is the optimum value? Actually optimum value is the maximum filter output value, that is indicated by the optimum value. Maximum filter will give you the maximum output. So the corresponding impulse response or transfer function of the corresponding transfer function of the impulse response is equal to h optimum of f equal to k into phi star of f into e raised to minus j 2 pi f into t. Okay, so for this optimum value of the transfer function, the matched filter will give you the maximum signal to noise ratio. Okay, so that is the value, and here take k equal to 1, then k equal to 1 means what will happen? H optimum of f equal to phi star of f into e raised to minus j 2 pi f into capital T. So H optimum is the optimum transfer function of the filter that maximizes the signal to noise ratio at t equal to capital T. So whenever the filter transfer function of the impulse response is h optimum of f, then it will maximizes the signal to noise ratio at a particular time, that is equal to t. And phi star of f is the complex conjugate of phi of f. Okay. So the impulse, see here is the Fourier transform value. So corresponding time domain value we can calculate. So time domain value is h optimum of t, that is obtained by inverse Fourier transform. So we have to take the inverse Fourier transform of h optimum of f. So h optimum of t equal to integral minus infinity to plus infinity h optimum of f into e raised to j 2 pi f t into df, that is equal to integral minus infinity to plus infinity phi star of f. We can substitute for h optimum of f, that is phi star of f into e raised to minus j 2 pi f into capital T into e raised to j 2 pi f t into df. So here e raised to minus j 2 pi f can be taken outside. So this equation become integral minus infinity to plus infinity phi star of f into e raised to minus j 2 pi f into capital T minus t into df. So h optimum for real valued signals, phi of t and phi star of f is equal to phi of minus f. If the signal is real valued, if it is having only real values, then phi of t and phi star of f will have a form phi of minus f. So we can simply substitute the value, that is phi star of f equal to phi of minus f. So h optimum of t is equal to integral minus infinity to plus infinity phi of minus f into e raised to minus j 2 pi f into capital T minus t into df. So that can be represented by h optimum of t equal to phi of t minus t. So that is the optimum impulse response or optimum value of the impulse response of that filter, phi of capital T minus t, that is the orthonormal basis function is shifted. Okay. So that is all about the signal to noise ratio calculation in matched filter. Okay, kindly go through the steps and you can make calculations. If you have any doubts, you can ask me through the comments. Okay, if you like this video, you can subscribe to my channel. Thank you.